pleasure to introduce our next speaker, Dr. KrisStarosta. Dr. Starosta is a nuclear physicist and associate professor at Simon Fraser University, a great university. He specializes in the structure of nuclei far from stability, nuclear shapes and shape coexistence, nuclear symmetries, nuclear fission, nucleosynthesis, and distribution of elements instrumentation for nuclear science experiments. He monitors iodine-131 in rainwater on Burnley Mountain and got a really good natural experiment coming his way shortly after the events in Fukushima, which he'll talk about.
Thank you very much for an opportunity to speak here. I probably will say things which may not necessarily be appreciated, but I need to tell them probably anyway. And to be specific, I would like to stress that what I'm going to talk about is the results in British Columbia. So whatever I'm talking about is particular to British Columbia, has nothing to do with Fukushima. We monitored in British Columbia and our data is representative for British Columbia. Okay. All right. If I would like to boil my talk to 3 points, here are the points. Point number 1 is that techniques to monitor radiation levels are well established and available at many places, including Nuclear Science Research Facility at Simon Fraser University, and we are in the Department of Chemistry, and this allowed us to do this measurement. And what we've done was that my team, the nuclear science team from the Department of Chemistry, followed the time profile of iodine-131 from Fukushima fallout from March 16, 2011 until mid-April 2011 in rainwater, and from March 15 to 2011 until early May of 2011 in seaweed. And then what we've done is we've done comparisons, and these are the comparisons which I would like to present, and these are comparisons to natural background radiation levels, literature data on previous accidents, medical doses used in diagnostic and treatments, and results of other measurements. And essentially, our conclusion was that there is no significant impact on the environment in BC. So there was a lot of talk about iodine-131. Iodine-131 is a man-made radioactive isotope of iodine. It's used in diagnostics and radiotherapy of cancer. Accumulates in thyroid, thus large-scale exposure is a potential health hazard, therefore the concern. Has a half-life of 8 days. It's not found in the atmosphere in normal conditions. So the normal atmosphere should not have iodine-131. It is an abundant fission fragment, and therefore, because of that and that, it's a good indicator of radioactive releases in reactor accidents. It is an easy target because it is not obstructed by the background. Now, before we go further, I would like to make this statement here, and the statement is that nuclear science provides access to some of the most sensitive and non-destructive measurement techniques, and this is the reason nuclear sciences are used in life sciences. Therefore, you're using a PET scan and you're using MRI and other devices in medicine. Now, if you consider 10 becquerel per liter activity of iodine-131, which was an average activity, or let's say the activity measured at SFU on March 19th, this corresponds to 10 to the 7th particles. So this is 10 million particles of iodine-131 per liter of water. 1 liter of water is 55.6 mole, or 3.3 times 10 to the 25th molecules. If you take the ratio, it tells you that we are sensitive to 10 to the 7th parts per 3.3 times 10 to the 25th, or 1 part per 3.3 times 10 to the 18, which means 3.3 times billion we see. All right? And that's why we've seen iodine-131 from Fukushima. What we look for is the characteristic radiation in gamma ray spectrum, and these are patterns which we can recognize. And this is an example of a signal. Blue is cesium-137, red is cobalt-60. You see the difference between blue and red. We can measure these patterns and we can identify the isotopes based on these patterns. We can identify the type of the isotope and we can quantify the amount of the isotope from this measurement. To do this, you need a sophisticated detection system. Okay, this is a well, let's say, maybe my colleague will take it as an overstatement, for my colleague is not sophisticated, but let's say you need to have more than a Geiger counter. This is the system which we have at SFU. It consists of a detector. Detector is cooled by liquid nitrogen. Detector sits in this shield. This is the LED shield, which screens the detector from environmental natural radiation, which allows us to see iron 131. This is the computer which runs the analysis. Now, the shield is crucial. Okay, for measurements in BC, the shield is crucial. If you measure without the shield, you see red. Red is the radiation which you are receiving from the background when you are looking at the slide and listening to my talk. That's the average BC background measured at Simon-Fraser. Okay, so this is what you're getting right now. If you use the shield, you see blue. And what you can see is that this is the counts per channel in logarithmic scale, and it shows you that we suppress the background by more than 100, by a factor of 100. So this is another picture of shields. This is lead, this is copper and cadmium, this is the detector signal in the shield. This is the signal which we've seen. This is the spectrum of gamma rays seen on March 18. This is the spectrum of gamma rays seen on March 20th. This is the spectrum of gamma rays seen on March 29th. This is the signal from iron 131. It is not present on March 13th. It is March 18th. It is present on March 20th clearly, and it fades away on March 29th. We can analyze its peak and its intensity, and we can quantify it. This is the time profile which we measured. As in the rainwater, this is specific activity in the rainwater. You can see no signal here. The accident is here. This is when we start measuring. You get an increase up to, let's say, if you want to take the upper end of the error bar, 16 becquerels per liter, decays down and goes to zero in let's say, April time. To increase our signal, because the signal in water was weak, we used by accumulation by seaweed. We collected seaweed samples, we crushed the samples, we reduced the volume, and we measured the samples. This is the signal in seaweed taken from North Vancouver. This is taken on March 15th. No sign of iron 131. This is taken on March 22nd, clear signal of iron 131. This is the specific activity in becquerels per kilogram. In seaweed, we have two sampling stations. One was North Vancouver in red, the other in Banfield Marine Science Center in blue. You can see the iron 131 in rainwater in two seaweed samples, so we clearly can identify that as signal from Fukushima. This is the overlap of the time profile in water with the time profile in seaweed. You can see the effect of bioaccumulation. Rainwater fades away quicker, seaweed accumulates and decays later. All right, comparison to natural background radiation. So let's compare 16 becquerels per liter in BC rainwater with natural sources of radioactivity. Living tissue contains 230 becquerels per kilogram of radioactive cosmogenic carbon-14. Since tissue is mostly water, this is 200 becquerels per liter. You can multiply by your mass, then you will get the number of becquerels per your body, and then you can compare this. So per liter of tissue, you have more carbon-14 by a factor of 10 than we detected in the rainwater. Radon to 22 concentration in groundwater is on the level of 5 to 300 becquerels per liter. Near uranium-rich deposits can reach 1,000 becquerels per liter. Milk contains 50 becquerel per liter of potassium 40. Tap water usually contains 1 becquerel per liter of radium to 22. Rainwater typically contains 4.3 to 5 becquerels per liter of tritium or hydrogen-free. Coal contains 4 to 300 becquerels per kilogram radioactivity of uranium and its daughters. If you do a calculations, 1 GeV coal-burning power plant releases typically 200 becquerels of radium to 22 per second. Natural background radiation, again, food let's take 400 becquerels per kilogram activity. This is top. This is higher limit of what we've seen. Iron 131 in BC dried seaweed with natural sources of radioactivity in food. Bananas contain 15 becquerel of potassium-40 per banana. Brazilian nuts 200 to 400 becquerels per kilogram of potassium-40. Lima beans 170 becquerel per kilogram of potassium-40. Vegetable 125 becquerels per kilogram of potassium-40. Red meat 100 becquerels per kilogram of potassium-40. Brazilian nuts 40 to 260 becquerels per kilogram of radium-226. You can take the 400 becquerels per kilogram activity of iron 131, which we measured in seaweed after Fukushima, and compare to what has been measured in Vancouver in seaweed after the Chernobyl. And this is the paper, you can look it up. And that's also a measurement of iron 131 in seaweed, in Fukushima seaweed after the Chernobyl incident, also done by SFU. This is the curve which they've measured, the daytime profile. This is in slightly different unit. They use becquerel per gram. 400 becquerels per kilogram corresponds to 0.4 becquerels per gram. So specific activities of iron 131 in BC seaweed after the Chernobyl accident peaked at 4 becquerel per gram. This means that the radiation levels in BC after the Chernobyl accident were 10 times higher than following the Fukushima accident. And there is no assumption here. This is pure data. Okay. Comparison to radiomedical doses. Iron 131 is administered for medical diagnostics in the range of million becquerel per procedure. So this is a mega becquerel for diagnostics. 10 becquerel, the amount of rainwater. So if you take the 10 becquerel per liter, the amount of rainwater contained in this dose is 100,000 liters or 100 tons. All right. You need to filter out 100 tons of water, rainwater, to get the medical dose for diagnostics. The medical dose for cancer therapy of thyroid is in the range of million becquerel at 10 becquerel per liter. This is 100,000 tons of water. Other comparisons can be made. We have this discussion already. It needs to converge to the dose. There is no consensus. I think that we are not going there. If you take other measurements were done also at Triumph, for example. Triumph measured rainwater and milk samples and checked the bottled water for pre-Fukushima control sample. Detection limit was 0.09 becquerels per liter. There was no result. The rainwater on April 4th was 0.4 becquerel per liter. Milk was tested, no iron 131 was detected, potassium was detected. This data is available at Triumph website. Before I start, I should give credit to my collaborators, which is graduate students at SFU, Ken Merkel from physics for sampling gathering from North Vancouver, Banfield Marine Science Center for sampling on Vancouver Island, other seaweeds, and salmon, and financial support for the radiation safety at SFU. And here are my concluding slides, and I think